Number 10, GRB 200-1209D, brightest of all time. October 9th, 2022. Detection Fermi Swift. On October 9th, 2022, the Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope jointly discovered an extraordinarily bright gamma ray burst designated GRB 200-21009A. The Fermi Gamma Ray Burst Monitor, triggered on the event at 13:16:59.9 UTC, marking the onset of prompt emission. Swift's Burst Alert Telescope detected GRB 200-209A later at 14:10:17 UTC and localized it to coordinates 19 hours 13 minutes 3.48 seconds, right ascension, and 19 degrees 46 minutes 24.6 seconds declination. This gamma ray burst is the brightest ever observed and is estimated to occur only once in 10,000 years. The exceptionally large fluence of this event saturated almost all gamma ray detectors during the main burst. The CONUS Wind spacecraft measured the event fluence as greater than 5 times 10 to the negative 2 ergs per square centimeter in the energy range 10 to 1000 kiloelectron-volts, higher than any previously observed gamma ray burst. Optical spectroscopy measured the redshift of the afterglow as Z equals 0.151, which implies a luminosity distance of 745 megaparsecs. GRB 2210009A has the highest total isotropic equivalent energy of 1.0 times 10 to the 55 ergs, and second highest isotropic equivalent luminosity of 9.9 times 10 to the 53 ergs per second based on its redshift. Observations made by the Swift Burst Alert Telescope instrument and Fermi Gamma Ray Burst Monitor showed that it was an extremely bright and long-duration burst. The prompt emission was categorized as a long gamma ray burst lasting more than 600 seconds. Photon energies of GRB 200-209A reached up to 18 tera electron volts, which was the first time that energies greater than 10 tera electron volts have been observed. A strikingly large number of very high energy photons associated with this gamma ray burst were observed by the Gamma Ray and Cosmic Ray Observatory LHAASO. Observations with the James Webb Space Telescope have confirmed that GRB 200-1098 was caused by a massive star undergoing a type ICE supernova similar to SN1988 BW. Lightning detectors in India and Germany picked up signs that the Earth's ionosphere was perturbed for several hours by the burst, showing just how powerful it was. GRB 221009A is only the 7th gamma ray burst known to have generated X-ray rings, and as of March 2023, a record 20 X-ray afterglow rings had been identified around the burst. Scientists have nicknamed this event the BOAT, an acronym for brightest of all time. It is certainly the highest fluence and peak flux gamma ray burst ever identified by a large margin. The physics governing gamma ray bursts of such extreme energy remains an area of active research with many unresolved questions about jet structure and emission mechanisms. Number 9, GRB 0809, 16 C most energetic gamma ray burst, redshift 4.35, energy 8.8 times 1054 ergs. GRB 0809 16C is a gamma ray burst that was recorded on September 16, 2008, in the Carina constellation and detected by NASA's Fermi Gamma Ray Space Telescope. The Fermi Gamma Ray Burst Monitor triggered on the event at 00:12:45 UT, initiating a cascade of observations across multiple instruments and wavelengths. The burst lasted for 23 minutes, or 1400 seconds, making it substantially longer than typical high-energy gamma ray bursts. The event was the first GRB detected by the Fermi Gamma Ray Space Telescope with high significance detection of photons at energies greater than 0.1 GeV. Observations by the Fermi Gamma Ray Burst Monitor and Large Area Telescope show that the burst has a single spectral form from 8 keV to 13.2 GeV. The afterglow photometric redshift of Z equals 4.35 plus or minus 0.15, based on simultaneous 7 filter observations with the Gamma Ray Optical and Near Infrared Detector, or GROND. Observations were done with the 7-channel Grand at the 2.2-meter MPI to ESO telescope, the Sirius instrument at the Nagoya Seiyao 1.4-meter telescope in South Africa, and the GMOS instrument at Gemini. The explosion took place 12.2 billion light-years away, which means it occurred 12.2 billion years ago, when the universe was only about 1.5 billion years old. The redshift of approximately 4.35 means that this GRB has the largest reported apparent isotropic gamma-ray energy release, EISO approximately 8.8 times 10 to the 54th ergs. This places GRB 080916 C among the top 5% most distant GRBs, and makes it the most energetic GRB known to date. The explosion had the energy of approximately 9,000 type Ia supernovae if the emission was isotropically emitted. More than 10 photons with energy above GeV were detected, with the highest energy one at 13 GeV in the observer frame. The emission above 100 MeV was approximately 5 seconds later than the emission below 100 MeV, and lasted much longer even after photons with energy below 100 MeV became undetectable. The burst also sets a stringent lower limit on the GRB outflow Lorentz factor, gamma min approximately 890, indicating that the jet material moved at nearly the speed of light. The gas jets emitting the initial gamma rays moved at a minimum velocity of approximately 299,792,158 meters per second, or 99.999% the speed of light. The source frame energy release is equivalent to 4.9 times the sun rest mass energy, representing a staggering conversion of matter into radiation. It was the most energetic gamma ray burst ever recorded, until GRB 220-109A was recorded in 2022, which ultimately surpassed this record. The extreme nature of GRB 080916 C continues to provide astrophysicists with crucial constraints on models of relativistic jets, particle acceleration mechanisms, and the physics governing the most violent explosions in the cosmos. Number 8. GRB 130427, a highest energy photon 95, GeV longest gamma ray duration, 20 hours. On April 27, 2013, the Large Area Telescope aboard the Fermi Gamma Ray Space Telescope detected an exceptionally bright gamma ray burst, designated GRB 130427A, setting multiple records that challenged existing models of these cosmic explosions. The burst produced the highest energy photon ever recorded from a gamma ray burst, at 95 GaE electron volts, an energy level that pushed the boundaries of what scientists expected from these events. At a redshift of 0.34, the 95 GeV photon was emitted at 128 GeV in the rest frame, meaning the photon had traveled across billions of light years before reaching Earth. GRB 130427A also exhibited the longest gamma ray duration ever observed, lasting approximately 20 hours, far exceeding the typical durations of even long-duration gamma ray bursts. The burst had the largest fluence and one of the largest isotropic energy releases ever observed from a gamma ray burst, making it an extraordinary event in the study of cosmic explosions. Its intrinsic luminosity reached approximately 3 times 10 to the 53rd ergs per second, and its relative proximity allowed it to reach the highest fluence observed in the gamma ray band. The burst was detected by both the Large Area Telescope and the Gamma Ray Burst Monitor aboard the Fermi spacecraft, providing comprehensive coverage across multiple energy bands. The Large Area Telescope is a pair conversion telescope that observes photons from 20 megaelectronvolts to greater than 300 GI8 Ensardian field of view, enabling detection of the highest energy emissions. The telescope detected high-energy gamma-ray emission from this burst for almost a day, including a 32 GeV photon detected after more than 9 hours, demonstrating the prolonged activity of the event. These photons were more energetic and detected at considerably later times than the previous record holder, an 18 GeV photon detected more than 90 minutes after GRB 940217, which had been observed by the Energetic Gamma Ray Experiment telescope aboard the Compton Gamma Ray Observatory. A minimum jet bulk Lorentz factor of approximately 450 was required for GRB 130427A, assuming emission of a 73 GeV photon detected during the prompt phase was unattenuated by pair production processes, indicating extreme relativistic velocities. Temporal and spectral analyses of GRB 130427A challenged the widely accepted model that non-thermal high-energy emission in the afterglow phase of gamma-ray bursts is synchrotron emission radiated by electrons accelerated at an external shock. The maximum possible photon energy prescribed by the standard external shock model was surpassed by the late-time high-energy photons detected by the telescope, forcing scientists to reconsider the physical processes at work. Scientists proposed alternative mechanisms to explain the extreme energies observed, including inverse Compton scattering and hadronic processes involving interactions between high-energy particles and photons. Long-duration gamma-ray bursts are an extremely rare outcome of the collapse of massive stars, and the properties of GRB 13427A were similar to those of the most luminous high redshift bursts, suggesting a common central engine across cosmic time. The burst provided researchers with an opportunity to study gamma-ray burst physics in unprecedented detail due to its brightness and the wealth of multi-wavelength observations obtained. Observations span from optical wavelengths through X-rays to the highest gamma-ray energies, allowing scientists to trace the evolution from the initial explosion through the extended afterglow phase. The mechanisms that allow gamma-ray bursts to produce photons at such extreme energies and sustain emission for such extended durations remain areas of active investigation, with GRB 130427A serving as a crucial test case for competing theoretical models. Number 7, GRB 190114 C1 TV Gamma Ray Burst Magic Telescope Detection, January 2019. On January 14, 2019, the gamma ray burst designated GRB 190114C was first detected by the Neil Gehrels Swift Observatory Burst Alert Telescope and the Fermi spacecraft at 20:57:03 Universal Time. The burst originated from a galaxy approximately 4.5 billion light-years away near the Fornax constellation. Spectroscopic observations revealed absorption features consistent with a redshift of 0.4245. The burst had a duration of 25 seconds according to initial Swift measurements, though Fermi measured the duration at approximately 116 seconds in the 50 to 300 kiloelectron-volt band. The highest energy photon detected by the Fermi Large Area Telescope was 22.9 gigaelectron-volts, recorded 15 seconds after the Fermi Gamma Ray Burst monitor trigger. The twin major atmospheric gamma imaging Cherenkov telescopes performed a historically rapid follow-up observation, approximately 50 seconds after the Burst Alert telescope trigger, detecting very high energy emission greater than 300 gigaelectron-volts, with a significance of more than 20 sigma in the first 20 minutes of observations. Gamma rays were observed in the energy range 0.2 to 1 teraelectron, from about 1 minute after the burst at more than 50 standard deviations. The major atmospheric gamma imaging Cherenkov telescopes recorded the most energetic photons ever observed from a gamma ray burst. The MAGIC observations covered the period from about 1 to 265 minutes since the start of the burst, during which researchers observed gamma rays in the energy range between 0.2 and 1.0 teraelectron-volts. The 1-second peak photon flux measured by the gamma ray burst monitor was 247 photons per second per square centimeter, with a total fluence of approximately 4.433 times 10 to the negative fourth ergs per square centimeter in the 10 to 1000 kiloelectron-volt band. At the measured redshift, the total isotropic equivalent energy released in the rest frame combined energy range of 1 KO electron-volt to 10 gigaelectron-volts was approximately 3.5 times 10 to the 53rd ergs. The afterglow light emitted soon after the burst was found to be teraelectron-volt radiation from inverse Compton emission, identified for the first time. Scientists have proposed that inverse Compton scattering is the mechanism responsible for producing the teraelectron-volt photons observed in this event. The higher detection threshold for magic came due to the large zenith angle of the observation exceeding 60 degrees and the presence of a partial moon. After an initial flash of very high-energy gamma-ray photons, the very high-energy emission quickly faded, as expected for a gamma-ray burst, and corroborating the connection between the very high-energy flash and the burst. Multiple space-based instruments, including Integral, InSight HXMT, CONUS Wind, and Agile, also detected the burst across various energy bands. The detection marked a breakthrough in high-energy astrophysics, as researchers had been attempting to observe such very high energy emission from gamma-ray bursts for many years without success. The physics governing the production of such extreme energies in gamma-ray burst afterglows continues to be studied and refined by the scientific community. Number 6. GRB 250702. B longest gamma-ray burst ever observed, 7-hour duration, July 2, 2025. Gamma-ray bursts are among the most powerful explosions in the universe, second only to the Big Bang itself, and typically flash and fade within seconds to minutes. On July 2, 2025, astronomers were alerted to an event designated GRB 25070, 2 billion, that exhibited repeating bursts and lasted over 7 hours, making it the longest gamma-ray burst humans have ever witnessed. NASA's Fermi Gamma Ray Space Telescope first detected GRB 250702b, marking a record that nearly doubles the duration of the next longest known burst. Among roughly 15,000 gamma-ray bursts observed since astronomers first discovered the phenomenon in 1973, none are as long as GRB 272b, and only half a dozen even come close. Shortly after space-based telescopes detected the initial bursts in gamma rays and pinpointed its location in X-rays, astronomers around the world launched campaigns to observe the event in additional wavelengths. Infrared observations acquired by ESO's Very Large Telescope established that the source of GRB 250,702 billion is located in a galaxy outside of ours, which had remained a question until then. The host galaxy is located roughly 8 billion light-years away, so far that its light takes 8 billion years to reach Earth. A team led by Jonathan Carney of the University of North Carolina at Chapel Hill used 3 of the world's most powerful ground-based telescopes, the Victor M. Blanco 4-meter telescope and the twin 8.1-meter International Gemini Observatory telescopes, to study the event. These observations began roughly 15 hours after first detection and continued until about 18 days later, tracking the fading afterglow across multiple wavelengths. The team presented their findings in a paper published on November 26th in the astrophysical journal Letters, revealing unprecedented details about this extraordinary cosmic event. High-resolution images from the Hubble Space Telescope and James Webb Space Telescope revealed that the burst emerged nearly 1900 light-years from the center of its host galaxy, near the edge of its disk. This location eliminates the possibility that the burst was associated with a supermassive black hole at the galaxy's core, ruling out one potential explanation. The host galaxy itself is surprisingly large, with more than twice the mass of our own Milky Way galaxy, which is unusual since most gamma-ray bursts originate in smaller galaxies. The explosion occurred behind enormous amounts of dust, meaning even the power of the Webb telescope was not enough to see the expected supernova that might have accompanied the event. One unusual feature is that X-ray emissions were detected a full day before any gamma rays arrived, preceded by precursor activity that suggests a complex sequence of events. Despite numerous studies, there is little consensus on the origin of GRB 250,702 billion. Beyond that, it involved an accreting black hole, with theories ranging from stellar mass to intermediate mass black holes. Researchers have proposed that this may be an entirely new form of cosmic explosion, one that does not neatly match any other high-energy transients observed in the past 50 years. The physics governing such ultra-long duration bursts remains not fully understood, and scientists continue to analyze the data hoping to reveal what produced this once every 50-year event. Number 5. GW1708, 1/7 neutron star merger gravitational waves, Kilonova AT2, 017 GFO, August 17, 2017. On August 17, 2017 at 12:41-004 UTC, the Advanced LIGO and Advanced Virgo gravitational wave detectors observed a binary neutron star coalescence designated GW170817. The signal was detected with a combined signal-to-noise ratio of 32.4 and a false alarm rate estimate of less than 1 per 80,000 years. The Fermi Gamma Ray Burst Monitor independently detected a gamma ray burst designated GRB 170817A with a time delay of approximately 1.7 seconds with respect to the merger time. From the gravitational wave signal, the source was initially localized to a sky region of 31 square degrees at a luminosity distance of 40 plus or minus 8 megaparsecs. The component masses of the binary were inferred to be between 0.86 and 2.26 solar masses, in agreement with masses of known neutron stars. The initial sky localization of the gravitational wave signal allowed electromagnetic observatories to identify NGC 4993 as the host galaxy. After several hours, a longer-lasting astronomical transient designated AT2017 GFO appeared, visible for weeks in the optical and near-infrared electromagnetic spectrum. AT2017 GFO was the first kilonova that could be extensively monitored in time both photometrically and spectroscopically. Spectral modeling of AT2017 GFO identified the R process elements strontium and yttrium, which conclusively ties the formation of heavy elements to neutron star mergers. The multi-messenger observation provided compelling evidence that such mergers produce a copious amount of heavy R process elements and can power short gamma-ray bursts. From the LIGO and Virgo data, researchers measured the two neutron star radii as 10.8 plus 2.0 minus 1.7 kilometers for the heavier star and 10.7 plus 2.1 minus 1.5 kilometers for the lighter star at the 90% credible level. The detection of this gravitational wave signal offers a novel opportunity to directly probe the properties of matter at the extreme conditions found in the interior of neutron stars. At the time of GW170817, the maximum distances at which the LIGO Livingston and LIGO Hanford detectors could detect a binary neutron star system were 218 megaparsecs and 107 megaparsecs, while for Virgo the horizon was 58 megaparsecs. The detection of electromagnetic counterparts, in particular of the kilonova and gamma ray burst, suggests a complicated evolution of the merger remnant with a possible hypermassive or supermassive neutron star phase and black hole formation. The blue and red components of AT2017 GFO have been interpreted as the signature of multi-component ejecta in the merger dynamics. Researchers combined the strong strontium ion absorption emission spectral feature and the blackbody nature of the kilonova spectrum to determine that the kilonova is highly spherical at early epochs. The multi-messenger observation of the August 2017 event marks the advent of multi-messenger astronomy, which combines gravitational wave and electromagnetic observations. The physics governing neutron star merger remnants is not fully understood, and observations continue to raise questions that current models cannot fully explain. Number 4. Crab Nebula Supernova 1054 CE Brightest Historical Pulsar Remnant Taurus. Chinese astronomers recorded a new star on July 4, 1054, bright enough to be seen in the daytime in the constellation Taurus. Astronomers in Japan, China, and parts of Europe observed the supernova for around 2 years. The supernova was visible during the day for 23 days and during the night for around 650 days. The Chinese described the star as 6 times brighter than Venus and about as brilliant as the full moon. Carl Otto Lampland announced in 1921 that he had seen changes in the nebula's structure. This eventually led to the conclusion that the creation of the Crab Nebula corresponds to the bright SN 1054 supernova recorded by medieval astronomers in AD 1054. The nebula lies in the Perseus arm of the Milky Way galaxy, at a distance of about 2.0 kiloparsecs or 6,500 light-years from Earth. It has a diameter of 3.4 parsecs or 11 light-years, corresponding to an apparent diameter of some 7 arc minutes. The Crab pulsar, a neutron star 28 to 30 kilometers across with a spin rate of 30.2 times per second, lies at the center of the Crab Nebula. The period of 33 milliseconds and location of the Crab Nebula pulsar was discovered by Richard the Vth E. Lovelace and collaborators on 10 November 1968 at the Arecibo Radio Observatory. At X-ray and gamma-ray energies above 30 keV, the Crab Nebula is generally the brightest persistent gamma-ray source in the sky, with measured flux extending to above 10 TeV. The nebula is expanding at a rate of about 1,500 kilometers per second, or 0.5% of the speed of light. Hubble has captured extraordinary details of its filamentary structure, as well as the considerable outward movement of those filaments over 25 years at a pace of 5.5 million kilometers per hour. Researchers find a convergence date for the radio synchrotron nebula of CE 1255 plus or minus 27. Both the synchrotron nebula and the optical line emitting filaments have been accelerated since the explosion in CE 1054, but the synchrotron nebula has been relatively strongly accelerated, while the optical filaments have been only slightly accelerated. Historical observations of the supernova imply a typical supernova luminosity, but contemporary observations of the remnant imply a low explosion energy and low ejectokinetic energy. Despite extensive studies, many questions still remain, such as the progenitor of the explosion and the explosion mechanism. Scientists continue to investigate these discrepancies between the historical brightness and the physical properties of the remnant using models that explore alternative energy sources beyond standard supernova mechanisms. Number 3. Cassiopeia, a supernova remnant circa 1679 expansion rate radio source. Cassiopeia A is a supernova remnant in the constellation Cassiopeia and the brightest extrasolar radio source in the sky at frequencies below 1 GHz. Its discovery as a discrete radio source was reported in 1948 by Martin Ryle and Francis Graham Smith, astronomers at Cambridge, based on observations with the Long-Michelson interferometer. In 1954, Walter Body and Rudolf Minkowski confirmed the radio source's association with an optical nebulosity observed at the Palomar Observatory, identifying it as the remnant of a supernova. The supernova occurred approximately 11,000 light-years away within the Milky Way. Analysis of its expansion velocities and geometry have allowed the explosion date to be estimated as 1681 plus or minus 19 years. Although the explosion must have been very powerful, no contemporary record aside from a possible sighting by English astronomer John Flamsteed in 1680 exists of its having been observed. Astronomy historian William Ashworth found out in 1980 that it was perhaps observed by John Flamsteed on August 16, 1680, who catalogued a star near its position as 3 Cassiopeiae. The apparent absence of widespread historical records may be explained by interstellar dust that absorbed optical wavelength radiation before it reached Earth. The expanding cloud of material left over for the supernova now appears approximately 10 light-years across from Earth's perspective. The average expansion rate of the X-ray bright ring between two epochs was found to be 0.20% plus or minus 0.01% per year, twice as fast as the expansion of the bright radio ring. Hubble Space Telescope images taken in 2004 were used to identify 1825 high-velocity ejectonauts through measured proper motions corresponding to transverse velocities of 5,500 to 14,500 kilometers per second. Observations through the Hubble Space Telescope have shown high-velocity outlying ejectonauts moving with the highest speeds occurring in two nearly opposing jets. Weaker radio emission associated with synchrotron radiation is seen extending to the location of the main forward shock, traveling at 4,200 to 5,200 kilometers per second. At 1 GHz, its flux density is decreasing at a rate of 0.97 plus or minus 0.04% per year. The James Webb Space Telescope survey of Cassiopeia A with NR-CAM and MIRI imaging revealed a web-like network of unshocked ejectofilaments, a thick sheet of dust dominated emission from shocked circumstellar material, and dozens of light echoes. The JWST images unexpectedly revealed a giant loop structure across part of the interior of Cassiopeia A, which was popularized under the name the Green Monster. Near-cam observations place new upper limits on infrared emission of less than 20 nanojanskis at 3 micrometers from the neutron star in Cassiopeia A's center. Researchers continue to analyze multi-wavelength observations from radio to X-ray wavelengths to understand the complex dynamics and structure of this young supernova remnant. Number 2. GRB 1-800-720 B-Multi-TV Gamma Ray Production 10 hours afterglow. Duration. On July 20th, 2018, the Fermi Gamma Ray Burst Monitor and Swift Burst Alert Telescope detected an exceptionally bright gamma ray burst designated GRB 180720b. The burst was classified as one of the brightest events ever observed by Fermi, ranking among the top 7 brightest occurrences recorded by the satellite. Observations with the Very Large Telescope determined the burst originated at a redshift of 0.653, placing it over 6 billion light-years from Earth. The prompt emission phase lasted approximately 48.9 seconds, a relatively long duration indicating the death of a massive star. 10 hours after the initial detection, the High-Energy Stereoscopic System Telescope in Namibia began observations of the burst location. The HESS observations continued for 2 hours from 10 to 12 hours after the trigger, capturing gamma rays in the afterglow phase. Analysis revealed a detection of very high-energy gamma rays with energies ranging from 100 to 440 gigaelectron volts. The detection achieved a statistical significance of 5 sigma, establishing the first confirmed observation of a gamma ray burst at these extreme energies by a ground-based telescope. The discovery came as a surprise to astronomers because the emission was detected so long after the initial explosion, deep in the afterglow phase. The isotropic energy released during the prompt phase was estimated at approximately 6 times 10 to the 53rd power ergs. Fermi's Large Area Telescope detected the highest energy photon at 4.9 gigaelectron volts, arriving 142 seconds after the trigger during the transition to afterglow. The very high energy emission observed by SHESS demonstrated that extremely accelerated particles still existed or were being created many hours after the explosion. Researchers have proposed that synchrotron self-Compton processes may be responsible for producing the observed sub-teraelectron-volt gamma rays during the afterglow. Alternative models suggest the interaction of high-energy protons with background photons in the synchrotron region could explain the multi-gigaelectron-volt spectrum. The X-ray flux had already decayed by 4 orders of magnitude by the time S detected the very high-energy emission. Multi-wavelength observations were conducted across the spectrum, from radio wavelengths to gigaelectron-volt energies, tracking the evolution of the afterglow. The physics governing the production of such energetic photons hours after a gamma ray burst remains an area of active investigation. This observation opened new avenues for understanding particle acceleration mechanisms and radiation processes under the extreme conditions found in gamma ray bursts. Number 1. GRB 190829, a multi-TeV gamma ray emission nearly 3 days post-prompt phase. GRB 190829A was detected by the Gamma Ray Burst Monitor on board the Fermi satellite on August 29, 2019 at 19:53 UTC, marking the beginning of an event that would challenge conventional models of gamma ray burst emission. The burst was also detected shortly thereafter by the Burst Alert Telescope on board the Neil Gehrels Swift Observatory, allowing multiple instruments to track this cosmic explosion across different wavelengths. The host galaxy redshift of Z equals 0.0785 corresponds to a luminosity distance of approximately 368 megaparsecs, making this one of the closest long gamma ray bursts ever observed. GRB 190829A was the third gamma ray burst detected at tera-electron-volt photon energies, but featured a smaller isotropic equivalent energy of approximately 3 times 10 to the 50th ergs. Compared to previous detections, distinguishing it from other very high-energy bursts. The High-Energy Stereoscopic System detected very high-energy gamma rays from the afterglow of GRB 1908-298 between 4 and 56 hours after the trigger, providing an unprecedented extended observation window into the burst's evolution. Observations with HESS started 4 hours after the burst when the source first became visible to its telescopes, beginning a multi-day monitoring campaign of the fading afterglow. The low luminosity and redshift of GRB 190829A reduced both internal and external absorption, allowing determination of its intrinsic energy spectrum, which was described by a power law with photon index of 2.07, plus or minus 0.09, between energies of 0.18 and 3.3 tera electron volts, revealing detailed spectral characteristics. This spectrum was similar to the X-ray spectrum, suggesting a surprising connection between emission processes at vastly different energy scales. The X-ray and very high-energy gamma-ray light curves showed similar decay profiles, indicating that both energy bands were tracking the same underlying physical process. The decay measured with the HESS telescopes up to 56 hours after the original explosion was very similar to the dimming found in X-ray studies using the SWIFT satellite, further strengthening the evidence for coupled emission mechanisms. HESS observed the event on 3 consecutive nights from 4.3 to 55.9 hours after the burst trigger time, making this the longest sustained detection of very high energy emission from a gamma-ray burst afterglow. Very high energy radiation was detected above 3 tera electron volts for the first night at 4.3 hours, above 1 tera electron volt for the second night at 27.2 hours, and for the third night no significant signal was detected, documenting the gradual fading of the highest energy emission. These similar characteristics in the X-ray and gamma-ray bands challenge gamma-ray burst afterglow emission scenarios, forcing researchers to reconsider fundamental assumptions about particle acceleration and radiation processes. Scientists have proposed various theoretical frameworks to explain the observations, including synchrotron self-Compton emission and photohedronic models involving interactions between high-energy protons and photons. The findings were published in Science Volume 372, page 1081 in 2021 by the HESS collaboration, documenting the remarkable temporal and spectral properties of the burst. The proximity of GRB 1908 29A allowed observations to reach unprecedented energies above 3 tera electron volts, energies that would be completely absorbed by extragalactic background light for more distant bursts. A rebrightening in the optical light curve at approximately 5 days was attributed to associated supernova emission confirmed by spectroscopic observations of the 10.4-meter Gran Telescopio Canarias telescope, linking the gamma-ray burst to the death of a massive star. The physics governing the production of multi-tera electron volt gamma rays, nearly 3 days after the initial explosion, remains an active area of investigation, with competing models attempting to explain how particles can be accelerated to such extreme energies in the expanding afterglow shock.